Okay, so I hope to have your exams graded and back to you on Friday. I don't have them done yet. If you ask me how they're going, I will say that you had 5 more points on your exam than when you asked me. So don't ask. I haven't started them yet, so I have no idea how I will. Today and tomorrow is going to be power grading day. Everything gets piled up at the end of the semester, but you know that better than I do. So so we talked about the mechanism for doing free radical halogenation last time. And what we want to do is we want to talk about how we predict products, what the major products are going to be, and this is one of the more complicated sets of reactions. So I do have an assignment for Friday, writing the mechanism of the reaction, which I'll outline at the end here. But we want to start with the idea that, remember, free radical halogenation, what we're doing is, if we react something with Br2 or Cl2, what we're going to do is we're going to replace a hydrogen on the alkane with a halogen. And then we're going to end up with HX, HCl, HBr as our other product. So the issue then is, for this reaction, we could do this with lighter heat. We're going to get a different major product if we use light or heat. We could end up with a different product if we use bromine or chlorine. But let's start with the idea of going back to where we were last week before the exam. What are the possible products of this reaction? And so if I'm looking through here, I could replace one of the CH3s with a let's just do it with a chlorine. So the first possible product that I could make is this one, which I'll call A. So what I like to do is I like to label the hydrogens over here as to which product they give me. So that's product A. That is going to be 1-chloro, 2-methyl, 1,2,3,4 butane. So every time we make a new compound with a new name, it's a unique product. If we make the product with the same name, then it will be a same product. Which leads us to, if I added the chlorine here, it would also be 1-chloro, 2-methyl. So whenever you have a branch point, if you have the same groups off the branch point, it's going to be give the same product. So if you go all the way back to the beginning of the semester with naming, when we had a branch point, it didn't matter which way we go. In this case, these two CH3s are going to give us the same product. So we have a grand total of 6 hydrogens that could give us product A. And then we'll come back to why that's important in a minute. Then we have a hydrogen off of here, which we could call B. So the product B is going to be having a chlorine there. So that's product B. Then we have hydrogens off here, which we can call product C. So then we'll have a chlorine there, which would be product C. And then finally, we could have a chlorine formed off of the NCH3, and we'll call that product D. When we first start out, sometimes people will think that the CH3s that I labeled A and D would give the same product. You need to check that. In this case, product A's name is 1-chloro, 2-methyl butane. Over here it would be 1-chloro, 1,2,3-methyl butane. So products A and D are different, and so therefore they will give different products. So we do this for any molecule that we have. the first thing we have to do is identify all the possible products, because the next question is going to be, what's the major product? And in order to determine what the major product is, I need to determine what all the possible products are. And so that's what I've done here. Okay. Does that kind of make sense to everybody? We'll do more problems as we go along. So the question is, what's the major product? It depends. What does it depend on? Whether it's chlorine or bromine, it depends on whether it's light or heat. So the next question then is, well, how do we determine what the major product is? And we have two things that are fighting each other here. We have what I call statistics, and we also have what's called selectivity. So statistics are the number of hydrogens that can be removed in the reaction. How many different hydrogens will give me product A? How many different hydrogens will give me product B? And so if we look at this, there are 6 A hydrogens. So as that Cl dot is running around solution, as it removes the hydrogen from A, one of those A hydrogens, that's going to ultimately lead to the chlorine going there in the mechanism. So there are 6 different hydrogens that could give me product A. Now this is new. We haven't used this analysis yet. There's 1 B hydrogen, there's 2 C hydrogens, and there are 3 D hydrogens. So over here, 6 hydrogens will lead to product A, 1 hydrogen to B, 2 to C, and 3 to D. Is that important? Yes, but it is just one factor that goes into this. So this is brand new. We have never taken into account the number of hydrogens that could be lost. Right? We didn't do this in E2. We didn't do this in E1. We will not do that in E2 and E1. We only do this here. So that's statistics. So if pure statistics were in charge of this reaction, A would be the major product, because it has the most hydrogens leading to that product. And product B would be the least percentage product. Okay? But that's just one factor. The other factor is the selectivity. And the selectivity is going to basically take into account what is the most stable carbon radical intermediate in this reaction. And so if we look at that, we could say, well, where did product A come from? Product A came from a primary radical. Product B came from a tertiary radical. Product C came from a secondary radical, and product D came from a primary radical. When it goes into this mode, it frustrates me because sometimes the pen draws itself and I can't go back and forth with slides as easily as it did. So I'm stuck here. All right, so primary, secondary, tertiary, and primary radicals. So selectivity then says what we normally work with. How many times have we done reactions where the major product has come from the more stable intermediate? Lots. Right? Carbocation, when we added H plus to a double bond, which end did we add from? The end that gave us the most stable carbocation. When we had the Br dot and we added that to the double bond in the free radical anti-Markovnikov addition, where did we add the Br dot? to the end that gave us the most stable radical. So we've done selectivity a lot of times. So if selectivity was totally in charge of this reaction, product B would be the major product because it comes from a tertiary radical. Okay. But what happens is that it's statistics versus selectivity, because these two factors are fighting each other. So we have to somehow figure out a way to predict what the reaction would be, what the major product's going to be, depending on if statistics are totally in charge or if selectivity is totally in charge, which the problem is selectivity is never totally in charge. But I can make statistics totally in charge. So how do we juggle these two things that are really fighting against each other? Okay, so that's how I'm going to have to predict the major product. So what people did was this. They did reactions. So for instance, they would take a butane and they would treat it with chlorine at room temperature. Now when you do a reaction, a free radical reaction at room temperature, you need light to break the two chlorines apart. So at room temperature we use light. And so what they did was they did this reaction. They said, well, there's two products that I can form, one chlorobutane and two chlorobutane. They would analyze these products mixture by GC, determine what the percentages are, and so they could determine what the percentage was, but that percentage is a mixture of statistics and selectivity. So if I know what the percentage of product, in this case, let's call the primaries A and the secondaries B, I can determine what the percentage of product A is and what the percentage of product B is. And so what they did was they said, well, I can't overcome statistics. A will always be favored 6-4. There's 6 total A hydrogens, there's 4 total B hydrogens. So I can't change that. As the Cl dot runs around, it's going to be encountering an A hydrogen 6 times and a B hydrogen 4. There's nothing I can do to counteract that. So that means my percentage has to take into account that factor. But what I'd really like to do is to normalize that out. So what they say is that the percentage of A is going to, I'm going to divide that percentage of A by 6. And I'm going to divide the percentage of B by 4. And if I do that, if I divide the percentage of A by the number of hydrogens, then what I'm going to get is I'm going to get what I call the selectivity. In other words, I'm going to get the part of the reaction that's totally based on the stability of the radical. So if I do this reaction and I make those two and determine those two numbers, by themselves they mean nothing. But if I took the percentage of A and divided it by the percentage of B, and that's actually not what I do, if I take the percentage of B divided by the number of hydrogens, and I take the percentage of A and divide it by the number of its hydrogens, what I end up with is I end up with a ratio of how fast can you form the secondary radical versus how fast can you form the primary radical. And so this ratio is what we call our selectivity. And that ratio, if you do this for a whole bunch of different problems or a whole bunch of different molecules, you'll end up with that ratio being, for chlorination at room temperature, you will end up with a ratio of around 3.4 to 1. And so what that means is that by removing the number of hydrogens, I'm removing the statistical effects on the reaction. I'm just saying, you know what, when you do chlorination at room temperature, you form a secondary radical 3.4 times faster than you do a primary. And so we do this reaction again with tertiaries, and what we find is that we can basically have these selectivity numbers for all of these, for all three positions. So the selectivity of chlorination at room temperature turns out to be 5 to 3.4 to 1. That's, you form a tertiary radical 5 times faster than a primary, and you form a secondary 3.4 times faster than a primary. And that makes sense, right? We should form a tertiary radical faster than a secondary or a primary, because the tertiary radical is more stable. So you can go through this and find this ratio, and then we just rearrange the equation to figure out what our major product is. Okay. So the way we calculated this was we calculated this by saying, well, we took our percentage of product A, divided it through by the number of hydrogens that give us product A, and that gave us this selectivity. If I rearrange the equation, I can say I can calculate what the percentage of A would be by taking the selectivity and multiplying it by the number of hydrogens that give that product. And then what I do is I apply this formula to the molecule, and the position with the highest number is going to be the major product. So the numbers, I use 5 to 3.4 to 1. They may be a little bit different in Top Hat, but I will give you these for the exam, and I give them on the practice problems that are online, so that we're going to use these to figure out what the major product would be. Because I can't completely ever get rid of selectivity. Okay. So here's an example. So let's go back to this problem right here. Let's go back to butane, do chlorination at room temperature with light. What would be the percentages of 1 chlorobutane and 2 chlorobutane that I would get for that reaction? And what would be the major product? So what I do is I take my butane and I say I have A hydrogens and I have B hydrogens. I'm going to do this at chlorination at room temperature, and that's what RT stands for. And I'm going to do this with light. So sometimes you will see light as abbreviated as HNu, right, which is the general chemistry equation, energy equals HNu. So that's the energy of a photon, so we can write HNu as light as an abbreviation. And so I'm going to make 1 chlorobutane, so 1, 2, 3, 4. So 1 chlorobutane, which I'll call product A, or I could make 2 chlorobutane, which I will call product B. And so if we wanted to calculate the numbers for product A, I would say, okay, the percentage of A is going to equal the selectivity for A. What kind of hydrogen gave me product A? A primary one. So that selectivity is 1. It's always 1 for a primary system, because the way we do it is we take everything as a ratio to primary. So primary has to be 1. Then we multiply that by the number of hydrogens that give us product A. That's 3 on this side, and that's 3 over here. So that's 6. So I get a number 6. It's not really a percentage, but that's the number. So then we do this for B. We say, what is our, percentage, or what's our number for B? Well, how many hydrogens give us product B? There's 4. So I got 4 hydrogens, and what kind of hydrogen is replaced to give me product B? Secondaries. And so what's the selectivity for secondary? It was 3.4. And so 4 times 3.4 is 13.6. And so that would be the number for that product. And now what we do is we say, okay, for chlorination at room temperature, who has the bigger number? 2-chlorobutane. So 2-chlorobutane will be the major product of this reaction. And that takes into account the fact that the 1-chlorobutane is statistically favored, but 2-chlorobutane comes from the more stable carbocation, or the more stable radical. So in this case, the more stable radical outweighs the number of hydrogens. So we've got 13-6. If I wanted to know the percentage of this, the rough percentage, I would say that product B is 13.6 out of 19.6 times 100. That would give me the percentage. And over here, it would be 6 out of 19.6 times 100%, because I added 13.6 and 6 to give me the total value. Okay. So in this case, it would be what? 2/3, roughly 2/3 B and 1/3 A, give or take. Julie?
Did you say that top part would be given to us for the exam, the 5?
Yes, I always give that. I always give that to you. Now, this is just for chlorination at room temperature, because there's going to be other numbers for other reactions.
But we won't have to do the first math that you showed to derive it.
Oh no, I'm just showing you where it came from.
Oh.
So someone else, actually a bunch of people, have done different reactions and calculated. So these values, the reason they change is because they're an average of different reactions that we do. And ideally, the reaction has to have a primary, because we have to have that always, it's always related to 1, which is the primary. So the selectivity is interpreted as how much faster you form the radical versus of a tertiary versus a primary. But everything is always related to primaries. Okay. But then when we reverse the equation, we can now use it to calculate who would be the major product of the reaction. And we can get estimates of what percentage it would be. So in this case, the percentage would be 2/3 B and 1/3 A, if I do chlorination at room temperature.
Did you also use these to find the antimeric excess?
No, the different topic, different chapter, different equation. What this has similarities to is it has similarities like when you're calculating percentages to like what we do in GC, right? We divide through by the total number. So yes, we're dividing stuff in an antimeric excess, but different problem. Okay. So we can calculate that percentage. And we'll come back and we'll do that. All right. Everybody kind of with me? So this is the way that I can take into account both the stability of the radical, which is contributing to the major product, but also the statistics, which is contributing opposite of that. And so this takes into account both to give me what would be the major product of this reaction. Now, there's a problem. It's not really a problem, but it is. There are different selectivities for different reaction conditions. So if you do that same analysis to do bromination at room temperature, what you find is that the selectivities, again, will be tertiary to secondary to primary. They turn out to be 1700 to 80 to 1. So when we do bromination, our selectivities are much different. And the interpretation of that is that I can form a tertiary radical 1700 times faster in bromination than I can a primary radical. Now let's apply these numbers to that same reaction we just did, and then we have to talk about why the numbers are different. But if I took that same butane and I now react it with bromine light at room temperature, I'm still going to get basically the same products. I'm going to get 1 bromobutane and I'm going to get 2 bromobutane, products A and B. But now if I go through and I calculate their numbers, we're going to have, for A, 6 hydrogens give me A, times a selectivity of 1, because A comes from a primary radical, or from a primary hydrogen. And B, there are 4 hydrogens, but it comes from a secondary radical, a secondary hydrogen, which is now 80 for its selectivity. So now I have a 6 to 320 as the numbers. B is still the major product, but now it's 320 out of 326, and product A is only 6 out of 326. So that's going to be greater than 99%, and that's going to be less than 1%. Or maybe it's 2%. We'll make it less than 2% and 98%. Yeah, 1% of 320 is 3.2. Big difference, right? So this has implications for wanting to do this reaction. I usually say at this point, well, if you were working at a company and somebody said, hey, I want you to sell us, or I want to buy a 2 halo butane. And you would look at this and you'd say, well, if I want to minimize my side product, I would do this reaction with bromine at room temperature, because then I would make 98% of the product that I want to sell. And only 2% would be waste. If I did it with chlorine, I'm going to have I'm going to have a third of my product as waste. Or I find somebody who wants to buy the 1 halo butane, and then I can do it either way and sell off the waste. So there's a huge difference here in selectivity, which translates to a huge difference for bromination versus chlorination. As a matter of fact, if we think about the number of hydrogens as offsetting or counteracting the selectivity, if you have just secondaries and primaries, you need 80 primary hydrogens to break even with the 80 selectivity of the secondary position over the primary, just mathematically. Well, you're never going to have 80 secondary or 80 primary hydrogens. So for bromination, if there's a tertiary position, that's where the bromine's going. If there's no tertiary position, it's going to the secondary position. What if there's more than one secondary position? The one with the more hydrogens is the major product. But with chlorination, we actually have to run the numbers because you only need 3.4 secondary or 3.4 primary hydrogens to overcome a secondary position. Or looking at it the other way, you only need 5 primary hydrogens to overcome a tertiary position. Well, actually, in this case, we had, if we did the product we did earlier, we had primary hydrogens where there were 6 of them. So those 6 could overcome the 5 selectivity very easily. So with chlorination, we always have to do the quick calculation. For bromination, it's like tertiary position, that's where the bromine's going. Because it's 1700 to 1 favoring. So with these numbers, we can calculate what the percentages would be. We can calculate what the major product is. The only thing that people sometimes will get confused about with this, and I bring it up even though probably somebody's going to get confused because I said don't be confused by this. The numbers of hydrogens always come from the reactant. I won't give you the alternative to confuse you. The numbers of hydrogens always come from the reactant. So when I'm talking about 6 or 1 or 4, I'm always counting up the number of hydrogens in the reactant. So this is how we can use selectivity and the number of hydrogens together to calculate what the major product would be. You'll always know what the selectivities are. You'll have to count the number of hydrogens. You'll have to determine what primary, secondary, and tertiary hydrogens are, which hopefully at this point is a piece of cake. Because if it's not, you're going to struggle on this. So that's how we calculate what the major product is going to be. And what you can see is that with the selectivities being different for chlorination and bromination, you can get different major products depending on whether I do chlorination or bromination. Everybody's kind of with me here? So let me throw a second monkey wrench into this. What happens when we go above 300 degrees Celsius for either chlorination or bromination? So if we do the reaction at greater than 300 degrees Celsius, our tertiary to secondary to primary ratio is 1 to 1 to 1. So when you go up to 300 degrees Celsius, there is no selectivity. You form a tertiary radical as fast as you form a primary radical, or nearly as fast. So in this case, greater than 300 degrees Celsius, the product is totally based on statistics, the number of hydrogens in that position. So if I was to take I take my butane, I'm going to do chlorination now at greater than 300 degrees Celsius. I'm going to end up with the 1-chlorobutane and 2-chlorobutane, product A and product B. If I run the numbers, it's going to be 6 hydrogens times a selectivity of 1. This is going to be 4 hydrogens times a selectivity of 1, because now at greater than 300 degrees, the selectivities are both the same. And so I'm going to get a 6-to-4 ratio, but notice now I'm favoring 1-chlorobutane versus 2-chlorobutane. Before, 2-chlorobutane was the major product, now 1-chlorobutane is. So I've switched major products. for product A. I do need, and let me just point out something here, because this is, well, you won't be writing these. You'll be multiple choice guessing on them. Hopefully not guessing, but choosing. Yes, what I just did was a common mistake that people make when they're going quickly is 1, 2, 3, 4. You always want to make sure when you add that halogen to the primary that it gets its own bond. Otherwise, you do forget a chlorine. So just consider that me showing you a mistake that you could make, or me just making the same mistake, either one. Okay. So I switched the major product. It's now A. But notice that because it's pure statistics, if somebody walks into my company and says, "Hey, can you make me 1-chlorobutane?" And you go, "Well, I guess the best I can do is this free radical halogenation. I'm only going to be able to make it 60% yield. The other 40% is going to be 2-chlorobutane. So I'm either going to have to think about doing a series of reactions that'll get me a higher than 60% yield, or I'm going to have to find somebody else to buy the 2-chlorobutane. Because the best I'm going to be able to do is make it 60%. And in lab, we're like happy when we get a 25% yield, but that means we had 75% waste. If we're at a plant, that 75% waste is going to be like 3 tanker cars of waste that we're not going to be in business, because that waste is going to bankrupt us, because it costs more sometimes to dispose of chemicals than it does to buy them to begin with. This is an issue we have down when we buy chemicals in the stockroom. We have to dispose of them, and so we have to be careful we're not a profit business, but we're also not a bankruptcy business. So we want to make sure that we're not buying stuff that's going to cost us more to dispose of than to use, unless there's a very good justification for that. So this is how we can adjust the ratios. But now we have a big problem. Okay. So the selectivity changes as a function of temperature and as a function of whether it's chlorine or bromine. And what's changing is the rate of forming the radical. And the big question here is why? Why is all of this stuff changing? Because the math is pretty straightforward, but the reasoning behind that is a little bit more complicated. And what complicates it is, so the reason that we're saying that the stability of the radical is what's important in selectivity is because in my free radical mechanism, it must be then that the rate determining step is the formation of that radical. So remember, if we made a Cl dot and we reacted it with our butane, which 1, 2, 3, 4, that it's the rate determining step must then be the formation of this radical and HCl. And we would have the same rate determining step for bromination, and we would have the same steps just at a higher temperature. So the difficulty here is, why can I form at room temperature? Why do I form I gave you a primary radical. I should have probably given you tertiary. But why do I form one radical so much faster with bromine at room temperature than I do with chlorine? Because they're the same radical. So if they're the same radical, then how am I forming it faster depending on the reaction? Well, the first fact is, and books usually go into the actual numerical calculations of these, when you do this reaction with chlorine, this is an exothermic reaction. And with bromine, it's an endothermic reaction. And if you want to prove that, the book gives you bond association energies, and it goes through the calculation. But the nuts and bolts of this is chlorination is exothermic, but bromination is endothermic at room temperature. What does that have to do with anything? Well, let's imagine that you're going to form a tertiary radical. If I'm going to form a tertiary radical from using chlorination or bromination, first of all, the alkanes, the initial reactant for, let's say, chlorination and the reaction with bromination, the initial reactants are the same, but that's not true when we go to this actual reaction. So if I'm going to form a tertiary radical, for chlorination, the reaction is going to be exothermic. What does that mean? That means that the initial Cl dot and alkane are overall higher energy than forming the tertiary radical plus HCl. And if I'm going to do it with bromine, the initial bromine dot plus the alkane is going to be lower in energy than forming the radical NHBr. So exothermic reaction, endothermic reaction to get to the same place. Well, which one of those two reactions is going to occur faster? We go back to the Arrhenius equation, which says that the rate equals AE to the minus EA over RT. That's the Arrhenius equation. The Arrhenius equation tells us how the temperature affects the rate of the reaction. It tells us how the activation energy affects the rate of the reaction. So which one of these two reactions has the smaller activation energy? The exothermic one. Which one has the larger activation energy? The endothermic one. So chlorination has a lower activation energy. It will occur much faster than the bromine. Now, everybody see that? So chlorinate, you'll form the radical faster in chlorination than you will in bromination, because chlorination is exothermic and bromination is endothermic. But that's not what we're looking at. We're looking at, why do you form a tertiary radical so much faster in bromination versus so much, well, why do you form a tertiary radical so much faster than a primary in bromination versus chlorination? So this just tells us, well, you form a radical faster in chlorination than bromination, and whoop-de-doo. What's more important is how does the endothermic and exothermic affect the rate of reaction now when I say, okay, this is an exothermic reaction to form a primary radical, this is an exothermic reaction to form a tertiary radical. And then over here, for my bromination, which I'm going to screw up, I'm still going to have the same energy for the primary radical, and I'm still going to have the same energy for the tertiary radical, but now I'm going to have to go like this and like this to do it endothermically. And so in order for us to understand this difference, we have to go back and think about the Arrhenius equation, we have to think about temperature, and we also have to think about the Hammonds postulate, because if you remember back when we talked about Hammonds postulate, which was 1 to 3 months ago, what we said was that when you lowered the energy of the product, that you lowered the activation energy. And so we have, in order for us to explain this, we have to think about, okay, how much difference is there? And it turns out that there's less difference over here in the exothermic. So I didn't draw these to scale, but there's going to be less difference in the activation energy for an exothermic reaction. And there's going to be more difference in the activation energy when the reaction is endothermic. Those little differences in activation energy are amplified because it's the rate equals A times E to the minus EA. So everything is logarithmic here in the Arrhenius equation. So a little bit of difference, so the smaller differences in exothermic mean that the rates are going to be more comparable. Over here with the endothermic, those differences are going to be bigger, and they're amplified by the logarithmic function so that the rates of forming the tertiary radical is going to be much, much faster. So it's the exothermic versus endothermic that affects the rate difference. And I will just add one thing and then we'll talk more about this. It's a hiker-bird analogy. Right, so hikers and birds have the same energy. These two mountains are pretty similar in energy. It's going to go over them relatively the same rates because they're small mountains. Birds of equal energy are going to go over bigger mountains. They're going to be more selective and they're going to go over the smaller big mountain faster than the bigger big mountain. And then we have to use that analogy for temperature because the birds are either hypersonic birds with lots of energy or they're near death trying to float over the mountains. So we'll finish this up on Friday. But if you have any questions about any topics, Friday would be the time to ask. In the last folder, there are some review questions, multiple choice. The answer keys are there. If those are going to be good practice problems for the final exam. So any questions, put them on Piazza. You can start doing that. Bring them to class. We'll finish this up and then review for the final exam on Friday. What?